Every high-performance Rust program starts right here. But no matter how complex your logic gets, it all boils down to 4 atomic building blocks. Your scalar types: integer, floats, boolean, and character. One variable, one absolute value. Let's break them down. We start with the bedrock of computation: integers. Rust violently split this domain into two: U for unsigned, pure unadulterated positive capacity, and I for signed, sacrificing one bit to plunge into negative space. 8 switches on. A U8 maxes at 255. Need negatives? Switch to signed integers. Rust sacrificed the leftmost bit to act as a signed flag. Welcome to 2's complement. Rust lets you scale your memory footprint perfectly. Need more space? Scale up to 16, 32, 64 or massive 128 bits. Without explicit declared, Rust defaults it to I32, optimal balance of speed and capacity. Writing memory allocators or indexing hardware: meet I size and U size. These are shapeshifters. Their physical size looks directly to your CPU architecture and depends on it. Hardcoding massive values: Rust protect your sanity. Inject underscores to separate digits. The compiler shreds them, or writes straight to the metal, hex, octal or binary. The bits never change. But what happens when you push a variable past its physical limits? Take a U8 maxed out at 255. Order the CPU to add one more. In C, this is undefined behavior. In Rust, it's strict interception. Compile and debug, and Rust plants tripwires. If an overflow hits, the thread panics. It crashes instantly against silent memory corruption. But in release mode, those guardrails are stripped for pure execution speed. Instead of panicking, Rust performed 2's complement, wrapping 256 rolls completely over, resetting back to 0. You must anticipate this. To explicitly tame overflow, Rust provides dedicated standard library methods. Use wrapping add, checked add to return an option, or saturating add to log the hardware maximum. You dictate the exact failure state. When integers are 2-digit unit fractions, Rust gives you two floating point primitives, F32 and F64. By default, it locks into F64, delivering the double precision at the exact same speed on modern silicon. Floats aren't magic. They are rigidly defined by IEEE 754 hardware standard. Slice open a raw F32 and 32 bits fracture into 3 distinct components. One single bit dictates the sign, 8 bits drive the sliding exponent, and 23 bits from Mantissa, locking in your absolute precision. Rust supports the standard mathematical forge: addition, subtraction, multiplication, and remainder. At compile time, these operators are melted down into highly optimized machine instructions. But division has a trap. Divide two integers, the result stays an integer. Rust doesn't round, it mercilessly truncates towards 0. Divide -5 by 3 and a decimal is severed. Need what's left behind? The remainder operator extracts exactly that. It slices the value down to its core division boundary, returning only the raw indivisible remainder, pure arithmetic certainty. Next, we strip logic down to its absolute binary truth, the Boolean. It holds exactly two states: true or false. This is the ultimate physical switch, and the core mechanism that dictates your conditional routing and control flow. But physically, how much space does this switch actually take? It holds a single bit of true or false information, yet Rust forces it into a full 8-bit byte. It pads the rest, guaranteeing perfect, high-speed memory alignment with your CPU fetch cycles. Finally, we arrive at the car type, marked strictly by single quotes. In older systems like C, a card is fragile, just one single byte to hold a basic ASCII character. But Rust's Char is an entirely different, heavily engineering beast. Wielding a massive 4 bytes, a Rust Char swallows the entire spectrum of human communication. It represents a raw Unicode scalar value, ranging from absolute 0 all the way to U plus 10 quadruple F. Not just A to Z, Rust natively supports accents, logograms, and emojis. But be warned, human intuition doesn't match Unicode scalars. We will tear into the brutal reality of UTF-8 when we hit strings. Integers, floats, booleans, characters. These are the 4 indivisible atomic primitives, the unyielding foundation that guarantees safety, precision, and speed right on the bare metal. But the real-world data is rarely this simple. What happens when you need to fuse multiple distinct values together, locking them down into a single, highly structured memory block? Next time, we bind these raw scalars into compound types. We will dissect the exact memory layout of tuples and arrays. Hit subscribe, drop a like and stay close to the metal. BareMetal out.